Okay, so now we're going to look at moving charges, which is effectively the magnetic effect of a current. We've already mentioned that magnetic field strength is described by magnetic flux density, the density of the field lines. It's got a symbol of B and it's got units of the Tesla. We're going to talk about that again. Magnetic fields are found around magnetic materials and also current carrying conductors. That is the main idea from today. Being a wire, if you've got a wire, there is a magnetic field around a wire, and we're going to try and work out why there will be a force on a current carrying wire when it's placed in a magnetic field. Okay, you may have seen this experiment in the lab, or a version of this experiment. This is a power supply. Connected to the power supply is a copper rod, another copper rod, and that goes all the way back to the other connection of the power supply. So you've got an electric circuit that's made up not of wires in the usual sense, but of three pieces of solid copper rod, and this wire here is free to move and roll up and down the other copper rods acting as a support. This whole thing is suspended between a magnet. So here you've got the two poles of a magnet, and what would happen is when I switch this power supply on, you will have seen it, that the copper wire, which remember is not a magnetic material, so the copper is not attracted towards the magnet, but the copper wire will move and it rolls along. And in the lab we got it to change direction by changing the orientation of the field and the direction of the current. Why does this happen? Well, these diagrams might help a little bit. This is our wire, and we've already said that there's a magnetic field around a wire in the shape of a circle, a circular magnetic field. This is our sort of horseshoe magnet, and we've got a north to a south pole here, so we've got magnetic field lines going across the page from left to right. If I just sort of draw those so you can see above, so that'll be the picture above. So here we've got circular field going around like this, and here we've got a more uniform field going across the page like that. If you actually add them together, if you imagine adding that to that, then what you would end up with is this field. Now this field is the combination of these two fields, and hopefully you can see that you've got a higher flux density here than you have here. So what's going to happen is that the wire that's in the middle, somewhere where the pointer is there, the wire that's in the middle will move because it's free to move, because it's got a higher flux density here, so a higher field strength here than it has at the bottom of the page, so you can see that it will move. So how can we remember the direction of this movement? Well, there is a rule called Fleming's left-hand rule, and this allows you to predict the direction if you know the current and the magnetic field. So if you use your left hand and you point it so that your thumb, your first finger and your second finger are at right angles, it can hurt a bit while you do this, so don't do it for too long. Well, basically your first finger is in the direction of the magnetic field, and remember this is from north to south. This is why the poles are quite important. The second finger is in the direction of the current. This is conventional current flowing, so we're not worried about the direction of the electron flow. This is conventional current from positive to negative. So if you point your first finger in the direction of your field, the second finger in the direction of the current, then by default your thumb will point in the direction of the motion. You can see there's a little silly way of remembering this, the M for motion, F first finger for field and second finger for current, but use that and you'll easily be able to answer questions in terms of the direction of the movement of the wire. Okay, this was a little practical you might have done in lesson where you tried to work out what affects this force. If you use this setup with a top pan balance with a wire going through it, then due to sort of Newton's third pairs, action and reaction, then if there is a magnetic force on the wire from the magnet, then there is a magnetic force on the magnet from the wire, and this would cause the magnet, which is on top of the top pan balance, to either push down more or rise up. Okay, it wouldn't rise up, but it would appear to have less weight in terms of the top pan balance. So you can use this experiment. You can vary the current, you can vary the length of the wire, and you can try and just increase the magnetic field by maybe having more bar magnets on the side. By doing this in the lab, it's quite easy to see that force is proportional to current and force is proportional to length. Harder with force being proportional to the strength of the magnetic field because it is difficult to measure the quantity B. But really you do come to this equation that F is equal to BIL, where B is the magnetic flux density, I is the current, and L is the length of the wire that's actually in the field. Looking at this, we can rearrange this, and this ties nicely in when we talked about the definition and the units for B, which is the Tesla. If we rearrange F equals BIL to B equals force divided by the current divided by the length, this gives us the units for the for B quite nicely, which is the Tesla, and the Tesla is a magnetic flux density of 1 Tesla produces a force of 1 Newton on each 1 metre of wire carrying a current of 1 amp at 90 degrees to the field. So you can see that the units for the Tesla are newtons per amp per metre, because you've got newtons per amp per metre.